section 10.3 part 2. We left off with this problem, so here is the way you will substitute it. I suggest you use the fraction tool on your calculator, enter it like that, and then the correct answer is 1,328,777. So next problem, I was explaining we're going to derive the formula for annuities, which are a way of saving, like a savings account, but instead of putting money every month or every year, you just put a certain amount of money once and you let it accumulate interest for a period of time. So with the sequence that we have here, we have A sub 1, A sub 2, and so on. And we realize the first term, A sub 1, is capital P, and the ratio is 1 plus R. 1 plus R, 1 plus R, 1 plus R. To differentiate the ratio from rate, we're using uppercase for rate, for ratio, and lowercase for rate. So now what I'm doing is I'm using this formula, which we learned during the previous class. And the formula is here, and that is the sum of a finite geometric sequence. So that is the same formula that we're going to use here. And I'm just using uppercase R to denote the ratio. Keep that in mind. So now I'm going to start substituting. So capital R is going to be replaced by the ratio that I have here, 1 plus R. Then we need that to the power n, and that divided by 1 minus the ratio again. So the ratio, remember, is 1 plus R. Let's see. What am I missing there, guys? Who said that? Alexis. Thank you, Alexis. Thank you so much. Okay, so yes, that's very important because that's going to change our formula completely. So it will be capital P times 1 minus. And what I'm going to do here is distribute this negative sign here. Can I do that? Yes. No, I cannot, because there's an exponent here. So that one actually stays the same. Let me see here. Okay. Now here, if we distribute, it will be 1 minus 1 minus R. So then the ones will cancel out, and we get just minus R. I'm going to need more space. Oh, and why are we using... Okay, now just for the purpose of this lesson, I'm just going to change, instead of using N, we're going to use T, because that was the last term we were going to have. You guys remember we established that? A sub T. So what I'm going to do is change N here and here with a T. Okay, so now that we got that out of the way, we got P times 1 minus 1 plus R to the power T bracket over negative R. Now, there is a trick to make the denominator be positive. How can I do that? Multiply everything by what? Negative what?
1.
Negative 1. And whatever we do to the bottom, we must do to the top. So if I do that, I will get the positive R on the bottom. And then on top, I could just, instead of multiplying the principal times negative 1, I can just distribute the negative 1 to here and here. And that will give me the following.
Do I just put the sign from everything?
Yes. Well, not everything, but the first one, the number one, and then the second sign will turn into a positive.
So not the other.
Not the ones inside, because those we cannot touch until we were to remove the exponent. Correct. Now, it looks a little ugly to me. I don't know about you, but I'm going to change it because addition is commutative, so it shouldn't matter, right? And divided by r. Now, that looks a little nicer.
For the purposes like solving it, it's obviously.
Yeah. Now, the formula that we got is the same formula that you see here. Except that here n is equal to 1. Meaning that the interest will be compounded yearly. The formula that we see at the bottom, you guys notice there is an r over n, and there is an r over n here, and there's also an nt here. And so if n was just equal to 1, if I was to substitute them here, we will have r over 1, t times 1, and r over 1. Yeah, so do you guys see why it's not really necessary to have the n? Yes. Yes. Now, when will we use the other formula, guys? When it is not 1. So example 2, 4, you could even say a 3, a 6, 5. That's not very common. 12, not really.
73.
No, 52,
Where are you getting these?
and 365.
It's because when you put money into a bank, they don't just randomly decide 11 times a year, oh, I'm gonna generate interest. So when it's 2, it's twice a year. When it's 4, it's like every 3 months. When it's 3, it's every 4 months. You know what I mean?
Oh.
Okay, so what the n represents is the number of times the interest is compounded in 1 year. So if n is equal to 2, that means that the interest gets compounded twice in 1 year. So how could we say that mathematically? Well, with a word. It will be semi-annually. Do I need double M and double N? I don't know.
I think so.
Okay, it's okay. We're not in English class. If n is equal to 4, that means it happens 4 times a year. Quarterly, very good.
We've done something like this, haven't we?
Yes, we did. Thank you, Biryani. We did in chapter 3 when we looked at this formula,
Yeah.
the compound interest formula. And if you notice, they are very similar, right? Very, very similar. What would you guys say is different from them?
It's subtracting 1, and then it's also dividing by the rate again.
What do you guys think this minus 1 is?
The fee.
Minus the original? No, not the original.
I'm going to look at the formula.
Wait, do you know or are you asking us? Oh.
I was asking you, but now I'm thinking that I need to revisit the definition of an annuity, so I can tell you the truth and not make something up. Okay, then, so 3 times a year, that means that it happens how often? How many months?
3, 4.
Triangle.
I was gonna say that.
Every 4 months. Maybe not very common, but I just wanted to throw it in there to show you that 3 and 4 are different. Quarterly will be every 3 months.
It sticks like half.
Biannually,
Oh, fine.
Annually,
monthly.
Monthly,
What's
weekly,
52? Oh, and
weekly,
daily.
daily, hourly, weekly, secondly.
so you won't, from daily, we actually go to something else
So that's the
Hourly.
continuous one.
continuously.
What's continuous to like a big number?
It always,
That was when we used to use this formula. This is actually what I'm doing with my algebra too.
Oh.
Yeah. And actually, the E, if you guys look at the poster up there, when you get a chance, look at what's on the table, and it's actually, I believe it's this part. Let me go.
Everything I can see. I'm not supposed to.
It's this part right here when n approaches infinity. So as n gets larger, the approximations get closer and closer to e, which e is an irrational number like pi. Thank you. 2.7 what?
2.
1.
I see.
And then what's the next digit? Crystal, can you see?
Can I get a calculator?
No, it's too late. I'm too short.
Okay, Sean, tell us the numbers.
you're gonna make it.
Why don't you do that shit, since apparently he has a really good eyesight.
Bastian is in the restaurant.
It says-
Sean, what are the numbers?
It's it's up there. It's 2.7.
1.718281812.8.
Okay,
So it is 2.
Dot. Irrational.
Approximately 2.
We should have a pie day on February 7th.
I assume you can be shipping.
That's my birthday,
I
that's
know.
not happening.
Oh.
I mean, a pie day, an E day.
Sorry,
Karina.
This is 2.72.
You didn't have February
Because 1 8 rounded to 2.
That's really interesting.
You do something on my.
Okay, all right, guys. Let's finish this problem, please. How many more slots do we have? Are we almost there?
Can we go to break?
No, you guys should have gone during your
We have 6 more.
break. I mean, during your lunch.
Yeah.
Yeah, what is this?
Oh.
Not even back.
Okay, let's solve example 7. So we have at the age of 25 to save for retirement, you decide to deposit $200 at the end of each month. Okay, so I did explain annuities wrong to you guys. You keep putting money each month. You don't just let the money sit there. So you
Annuity and like the other.
say that again?
You said that annuity was different from something else, but so.
From just the savings account.
Oh yeah, so what's the?
Okay, so let me rephrase myself or correct myself. So the savings account, you just put the money in and you just let it accumulate interest. That was what we did in chapter
Oh, so you
3.
switched.
Yes.
You got that.
And then annuity, you keep putting money in after every month. And then Oleg, what you were mentioning is probably another type of
No,
annuity.
it's
Bastiana was the one that you take money at every month
Right,
out, like a trust fund, something like that. Uh-huh. So, and actually, if you take the money in or out at the end of the month or the year or at the beginning, it does matter. Dima, you have your cell phone? No. You have that face. I can see it.
Oh.
Face.
No, I'm
You've been texting. I can tell.
Yeah, it's like they're my cheeks.
Maybe meaningless.
No, she has that guilty face, but she has the phone there and there. Okay, so I'm going to copy the formula that we need. So we need to determine how much would you have there by the age of 65. So let's do this quickly, please.
So we should put 66.
Well, it says that whoever is saving is 25 right now.
Here you go. If you guys need to use the restroom, you could go, but come back quick, please. No, not all at once, one at a time. And it has to be an emergency.
I got got up first.
Okay, yeah, please. Alright guys, so we have here, let's just establish what each number represents. So the principal that we have here, or what's going to be going in, is going to be 200. Let's call it the payment. And then we have, of course, the rate, which is 7.5%. We have to convert it to a decimal, so it will be 0.075. And then we have the number of compounding periods. It says monthly, so that number, 12. And then T is for time, and so how many years are going to happen from age 25 to age 65? 40. Okay. All right, so let's go ahead and substitute everything. So we have 200 plus 1 plus 0.075 divided by 12, close parentheses, 12 times 40 minus 1, close the bracket, and the answer will be $604,765.
So we have to divide by R still.
Oh yes, I forgot to substitute that. So 0.075 over 12. I suggest you use your fraction tool, and then you're going to have to use it again, or, I mean, not really, for this one. That is still the correct answer, though. I just had it in my notes. After 40 years.
That's a lot.
It's a lot of money, and if you think about it, think about this. You are what, 16, 17? Yeah?
Yeah.
So, by the age of 25, assuming that you stay in college, what type of degree should you have? At least.
Math.
At least a bachelor's, right? Hey, if you all have masters, congrats to all of you. But, think about that. If you do have at least a bachelor's or a master's, or even if you are doing your residency as a med student, you could totally afford $200 out of your paycheck each month. And if you think about it, if you just do that, by the time you are 65, you will have this much to, like, I don't know, go to Europe or something. That's what I would do. Retirement. Yeah.
But doesn't, like, when you get that money out, don't you have, like, doesn't that money have interest?
Yes. Hey, I'm the teacher here. Andrea, to answer your question, there are types of annuities. So that's when you will consult with someone who doesn't have a degree only in math, like me. Maybe someone in finance. Yes, because there are annuities or retirement plans that, yes, they tax you. There are others that don't. There are trust funds that tax you, others that don't, even with college funds. Yes, Vivian.
What's the difference in an IRS and a 401k?
Oh, yeah, I do not know. Are you talking about IRS?
IRS.
That's the Internal Revenue Service. Is it like a government department? Agency? The ones that deal with all the money?
Okay. The 401k, you know.
401k is a retirement plan. Okay, so yes, lots of money. In fact, if you were to find a good bank with a good interest rate, you could probably do something that would make you $1 million by the time you're 60.
What kind of bank is 7.5? It's a lot.
Yeah, that's a little unrealistic, to be honest. Okay, next question. Now, geometric series.
Actually, Miss Moore, real quick, what is more realistic? Are you able to actually do this?
An annuity?
Yeah.
I used to have an annuity. I don't remember what it was, but it was something like in the twos.
7.5? That seems too good to be true.
Yes, it's too good to be true. Okay, let's stop talking now. Okay, now we know that there are two types of sequences, right? The finite and the infinite. So now the infinite ones, we're gonna call them infinite geometric series. And again, you will revisit this in Calc 2. So here, again, we're going to look at how we will add them, and this is the formula. Now, the formula is very similar to the other. Look at it. Can you guys look at it?
Yes.
Okay, so we have the first term divided by 1 minus r. And then I'm going to switch to the other one, the one for finite. What's the difference?
The 1 minus
This one
r to
doesn't
the
have
power of
the,
n.
one, yeah.
There's no 1 minus r to the power of n.
All this, right? That is gone when it's infinite.
Because that's the limiting factor.
Okay, so let's see. I think I was. Okay. Now let me tell you why the formula changes, just quickly. So if you were to keep getting more and more terms, this r to the power n will approach 0 if n was to get larger, like this. As n approaches infinity, r to the power n will approach 0. And so what do you get here? 1 minus 0.
1.
You get 1. And what is a sub 1 times 1?
A sub 1.
Just a sub 1. And that is, thank you, Miguel. That's what you get here, just a sub 1. So that's the difference with the formula. Now here, the condition is that the ratio needs to be a number between 1, less than 1, and greater than negative 1. So in the number line, it will be all numbers that are from here to here. Not only the 2 integers, the 3 integers, sorry, but everything in between, okay? Here we're including fractions. What do you guys think we cannot have a ratio greater than 1? Just think about it for 5 seconds.
We cannot have
Because there's
Let's take 5.
4.
Right, Sean.
I was going to say because there's absolute values right there.
Well, yeah. This right here statement is the same as this one. That's a fancy way to show it. Yes, Ezekiel?
So that's to be a fraction.
It has to be a fraction. Could we have a fraction like maybe that?
No. No.
Why not?
It's almost 2. It's almost 2.
Well, we'll think about what will happen to a sequence. Let's say I'm going to think big. R is equal to 100. What will happen if my first term was 100? What will my next term be?
100. That's the ratio.
It would be
No. This is geometric.
What's 100 times 100?
20,000.
4 zeros, guys. 4 zeros. What will be my next term?
A million. One more
6
zero.
zeros, guys. 6 zeros. And then my next term will be even bigger and bigger and bigger and bigger. So what will happen to my sequence? It will go kind of like out of control, and eventually it will reach that
The
infinite. Yes. So that's why we restrict that to only rate when the ratio is that. Okay? So we use the formula for the sum of an infinite geometric series. We need the first, right? We need the first, and then 1 minus r. Just don't talk, please. The first term and the common ratio. Okay, now the problem that we have here, I'll explain it quickly. what we have is a circle, and the circle was cut in halves, and then another half. One half was cut in half, and then this half right here was cut in half. So, what will be the ratio for this sequence size? Every term is being multiplied by what?
2.
Not by 2,
One half.
1/2. So we could say that the common ratio is 1/2. And the first term is 1/2, right? So if we were to keep doing that, just like keep cutting halves and halves and halves and halves and halves, eventually, graphically, you should get to the whole circle, right? So let's see if that sequence will actually equal to 1. So if we substitute in here, we'll have 1/2 divided by 1 minus the ratio, which is 1/2. Right here, we'll have 1/2 over, what is 1 minus 1/2? 1/2. What is 1/2 over 1/2? Is 1. All right, so now let's see that one right there. So we need the first term, which is 3 over 8. And what is the common ratio here, guys? Do you guys remember how to find it?
Negative half. Negative half.
So we take the second, divide by the first. Let's see if it's negative half. And what I'm going to do is just not multiply. I'm just going to leave them as factors. And you guys say negative 1/2. Very good. So negative 8 over 16, which is negative 1/2. Now, if we apply that to the formula says that the sum will be a sub 1, the first term, 1 minus r. So a sub 1 is 3 over 8 over 1 minus the common ratio, which happens to be negative 1/2. So if you put a negative 1/2 here, you're actually going to get 1 plus 1/2. So that will be 3 over 8 divided by, here is 2/2, so 3 over 2. Thank you. Okay, so just to finish this problem here, it will be 3 times 2 is 6, 8 times 3 is 24, 1/4, thank you. Okay, so yes, that's how you do that. Now, let's look at this not the last. Okay, we're almost there, we're almost there. Now, I love doing this problem. This problem costed me a B in college.
Really? That comes?
Yes.
1/3.
You know it's 1/3, right?
Why isn't it 1/3?
It is 1/3, but let's prove it. So, that, the first term, this number right here, if you didn't have the rest, what would that be?
3, 4.
How would you read it? 3 what?
10.
With a line over it.
How about the next one?
300.
300.
Oh. I get you.
And the next one?
3,000. 3, 10.
And so on, right? Now, here we could say this is 3/10, and then this one here is 3/10, but it's actually being multiplied by the ratio, which is 1 over 10. This third term is 3/10, the first one, multiplied by the ratio, which is 1 over 10 to the power 2, and so on. So what we can tell from here is that a sub 1, the first term, is 3 over 10, and the common ratio is 1 over 10. So the sum of the whole infinite sequence, the whole thing, even with the lines that you guys were mentioning, it will be the first term divided by 1 minus the ratio. The first term is 3 over 10, so we have 1 minus 1/10. So this is 3/10 over 1 is equal to 10 over 10, so 10 over 10 minus 1/10 will be 9/10. Bless you. So here, 3 times 10 is just 30, 9 times 10 is 90, and so that will be equal to 3 over 9, or just 1/3. Yes, that is the proof. The next one is exactly the same way, but you will set it up as 7 over 10, 7 over 100, and so on. So let's move on to the last one. A tax rebate that returns a certain amount of money to taxpayers can have a total effect on the economy that is, you know what, we will just leave this problem for next class. Or no, I will finish it and then post the video. Yeah, we cannot get any more behind. We can't.